Thank you very much, TBH, for inviting me to this talk. And thank you very much, my dear colleagues, for taking out your time to listen to me today. I'm going to talk about sequences in its natural habitat. इस टाइटल से तो बहुत सारे लोग पूछ रहे थे कि ये कोई बायो की टॉक है या कोई जानवरों की बात होगी, तो मैंने कहा कि नहीं, यहाँ पे मैथ की बात होगी, इसलिए हाल खाली रह गया. अच्छा, तो ये पहले तो मैं ज़रा इस टाइटल की वजाहत कर दूं कि हंटिंग अ सीक्वेंस इन इट्स नेचुरल हैबिटेट, इसका मतलब क्या है. इसका मतलब तो हम ग्रेजुअली जैसे टॉक के अंदर देखेंगे कि नेचुरल हैबिटेट हमने उसको क्यों कहा और हंटिंग का क्या मतलब है. तो हम शुरू करते हैं पावर पॉइंट की जो स्लाइड्स हैं वहीं से. तो okay, thank you. So, I am Sajjad Akbar and I have completed my M.Phil in mathematics from Salam School of Mathematical Sciences, Lahore. So today I'm going to talk about sequences, and by the way, I have to say that sequences, this topic was my title of dissertation. So that gives me confidence to speak on such a weird topic. So the target for today's talk is that I'm going to first introduce groups, and then I will talk about sequences, what are sequences, and then at the end I will talk about elliptic curves, and then we will see how sequences sit inside these elliptic curves. And this is a kind of a simple way, a picture you can look at how different branches of mathematics are interconnected, how we can bridge between two different branches of mathematics. For instance, in this case we are looking at geometry, which is elliptic curves, and for example combinatorics, which are the sequences, or maybe algebra, which is the group that is going to be there. So this is the target, and the agenda will be very simple. I will first define groups, then we'll delve into sequences, and then we'll see elliptic curves, and then we will at the end, towards the end of this talk, we will connect all the topics together. Sounds good? Okay, so before we go into groups, this talk requires actually to understand more about integers and rational numbers. So I will start by making integers into a group. So when we say we have set of integers, we have this set of numbers with -1, -2, and so on and so forth in both directions, and this is the set of integers that we take. And let's observe some of the properties of this set, and then we will convert these properties into a group. So the first thing we see in this set is that when we add two integers, we always get an integer. Okay, so that gives us the property number 1, which we call closure property. And also you can see that there is this element 0, which does nothing to any number when we add it to. Okay, so that number, this special number, we call this the identity element of this group. So we are actually making this set into a group. So this is playing the role of identity. Now we have, for every positive real number, positive integer, we have a negative integer such that together we add negative numbers to the positive, same numbers will give us 0, and that gives us the inverses. So this is our second, and this is inverses. Okay, and there is this fourth property, which is associativity, to say that whether we add 2 plus 4 first and then add 5 to this sum, which is going to be same as we add 2 and we add 4 plus 5 first. So we have this choice of putting these parentheses however we like. So if we say this number and that number, they are going to be same. So there are some cases where this does not work, but we are in the set of integers. So all these properties, this making the fourth property, which is associative property, and we call a set having all these four properties a group. Okay, this can be any set. This can, we will see that this can be some weird kind of sets. For example, in the diagram above, you can see that there is a triangle, and we are operating this triangle by rotations and flips along these red lines. So the operations actually are the elements of the set that we are doing. So we have this 120-degree rotation, which is an element of the group. Okay, and then we have this 240-degree rotation. So the same thing is happening here, that we add -1 to 1, giving us 0. When we rotate first it by 120 and then by 240, we are back at the identity. So that's the essence of capturing this closure property, that when we have two rotations, they will give us a third rotation. In this case, 120-degree rotation followed by 240 rotation gives us identity, so making this element inverse of this. So and similarly we have these reflections. They are self-invertible elements to call. So when we reflect this triangle twice, it will be back as it was initially. So this is the identity position we choose. So the groups, they at one end play a role in this axiomatic sense. In the second sense, they are there to capture symmetries. So for example, how we can relate this group of integers to symmetries, to say that these integers, they are translational symmetries. So when we have an infinite line with equal number of points placed on the line, and we translate it left or right, essentially captures the symmetry of the line. It doesn't change the shape of the line at all. And similarly, in this case, when we have an equilateral triangle and we rotate it by 120, it is same as before. We don't know otherwise. If we don't put these 1, 2, 3 on the vertices, we would never know that whatever we did with this. So there's the point of capturing symmetries with groups. So I would like to show you another group which is similar to the triangle, but now this is a square. And if I can play this, and now this is, you can see more visually. By the way, I took this clip from 3B1B, 3 Blue 1 Brown videos on group theory. You should check it out. So this was a short clip from that scene. But we are not interested in all of the group theory, but we are only interested in rational numbers. So I hope you all know rational numbers, and rational numbers satisfy all these axioms that we started with, and we try to generalize these axioms into these properties, the properties of integers into these axioms of closure, identity, inverses, and associativity. And rational numbers do satisfy all these properties, that we add two rational numbers, we get a third rational number. We have this 0 element. By the way, we can write 0 divided by 1 to make it into the class of rational numbers. So and we have inverses for every rational number. We have another rational number, which, so, and the associativity also is true. We don't need to prove this. So we are interested in rational numbers for today, not any weird group or no any fancy group of symmetries kind of thing. So let's see some other groups. There are many, but the point of this whole slide was to show you this abstract algebra book by Joseph Kalian, which is what you can start with when you are interested in groups or in algebra generally. So this is a simple undergrad book which you can read. Okay, so the next point I'm trying to talk on today is sequences. And for example, in the set of integers, we can make different, of course, if we eliminate these negative numbers, we have a sequence of numbers starting with 0, 1, 2, 3, and this itself is a sequence. So by the sequences are enumerated collection of objects that we can we have a one-to-one correspondence with the set of natural numbers, and we have a set whose domain is the set of natural numbers, and then it can be any range. So what I was talking about is, for example, here you can make new sequences by taking 2 and multiples of 2, 2, 4, 6, 8. There's essentially the even numbers, and these are sequences. By the way, this is ये असल में दो का पहाड़ा आप समझ लीजिए इसको कि हम दो को जो है ना एक सेट ऑफ नेचुरल नंबर्स के साथ मल्टीप्लाई कर रहे हैं. सो दिस नंबर कैन बी written as 2 times n. So n will be natural number, 2 times n will give us this whole sequence. There are different kind of sequences you can have. For example, we can define a sequence by adding 3 to the previous term to get the new term in the sequence, or even we can multiply with some starting point and defining the sequence by this formula. So the above formula can be written as every new term in the sequence will be given by the previous term, and we add 3 to this. And the second term is, of course, simply every new term of the sequence is 6 times the previous number. So this multiplication. So for example, this sequence of zeros, this is called null sequence. Not very interesting. Again, this is the same natural number, every natural number giving same itself back. So, and this is Fibonacci number. This is one of the most famous sequences of all time, and there is a bit of history to this, but we are not going to the history or the historical importance, but this sequence is easy to construct. So you start by 1, 1, and then to get the new term you have to add the previous 2 terms. So 1 plus 1 gives you 2, 2 plus 1 gives you 3, 3 plus 2 gives you 5, 8, 13, 21, and so on. So you just keep this sequence in mind, and up till now we haven't touch the area of elliptic curves. So let's bring the main topic of today's talk, which is elliptic curves, and we will see how elliptic curves are interesting. The first thing about elliptic curves is that when we start to study these algebraic geometric objects, we start by considering functions of 2 variables, f of x and y, and we start, of course, with the simplest case, that something like a, let's make it more symmetric, ax plus by equals c. So all these equations are classified as linear equations, and we know all the solutions to such equations. Any equation of this type will have a solution if a and b, the GCD of a and b divides c, to be technical, but I was told not to go into the details and technicalities, but just commentary on these objects. And then the second thing is, this is our first object, and the second object is when we go a degree higher. So that is, for example, if we take x square plus y square equals some number, let's say d, and these are essentially all the degree 2 equations are conic sections, and we have a classification of all the conic sections. But if we take it a degree further and we talk about the equations that contain cubic powers, x to the third power, y to the third power, and of course x, y square, and all the combination of lower powers of these without exceeding the degree 3. So these equations, they are essentially classified as the elliptic curves. And this shape over here is given by this equation, which is y to the second and x to the third minus. So these elliptic curves are classified by a and b. All the properties of these elliptic curves will be decided by choice of elements A and B. And if A and B are coming from rationals, we call these ellipticals to be defined on rationals. If they come from any finite fields, and so on and so forth. So elliptical is, here are some highlighted terms. The first one is ellipticals is smooth, projective, algebraic curve of genus 1. Well, these are too technical to explain, but smooth means that there is no self intersection. In short, in simple, self intersection of this kind, which is possible in cubic curves. So we eliminate all such curves which have a self intersection. All curves with a cusp, for example, this is given by y square equals x cube. So in technical terms, this cubic curve is not an elliptic curve because this is not smooth. So this is a point where the smoothness is not guaranteed. And this is projective because we kind of take the two infinite ends and tie them together in simple, so to make sense of projectivization. And genus 1 means this donut here you are seeing is this has one hole. So in simple, you can connect the genus to number of holes when we plot these curves over complex. So of course, for example, a minor detail that sine square plus cosine square gives you 1, and that is a parameterization of this circle. And there is a similar parameterization of this curve in terms of functions which are defined over complex, and when we plot them, they give you such beautiful objects which are called elliptic curves. And the number of holes of these objects will decide the genus of this curve. So an elliptic curve for us in today's talk will be a smooth curve which we can plot in two-dimensional plane given by an equation of this type. We will see how different choices of A and B gives us different shapes of these elliptic curves. For example, here B is 0, A is -1. We will get this curve. This elliptic curve has one component, and the other component, by the way, this is called the egg of elliptic curve. I have no idea why. This is when we choose A equal -1 and B equals 1. So these are two smooth elliptic curves. This is a reference text on elliptic curves. By the way, I didn't wanted to mention these references, but just focus on how he starts the forward. It is possible to write, Serge Lang writes, it is possible to write endlessly on elliptic curves. And further he says that this is not a threat, because he himself wrote almost 60 or more books on elliptic curves, and this elliptic curves Diophantine analysis is one of them. Yes, you must be shocked. So elliptic curves, they are let's see first how elliptic curves change shapes depending on the choice of A and B, and we are defining A and B from a set of integers in these examples, and because of this group law, we can define a group law on elliptic curves. The way, remember, we define group law on integers, combine two integers to get an integer and blah blah, or combine two operations on the symmetries of a regular polygon and to make it into a group. But this time we are having this very interesting aspect of ellipticals, that they naturally come with this group law, and this is not one can expect from these weird curves. So how we define the group law is, let's take example of this curve. We take 2 points P and Q on this elliptic curve, and we want to add these 2 points. And this curve being cubic, if we try to join these 2 points with a straight line, we always hit a third point. Okay, this is clear from here. But what about the line which is going from 1 point, and there is a tangent line? So it also hits somewhere elliptic curve at the third point. And again, remember, when I try to explain projectivization, I told you that the infinity and minus infinity and plus infinity, they are connected together, they are made same. And when we have a vertical line which is hitting on 2 points, it essentially hits the third point, which we call the special point, and the role of 0 is played by this special point. The two infinities, we make them 1, will be the identity of this group. So how we define the group law is, you can see in the slides, that we add P and Q, and we define that 3 points lying on this straight line will be equal to 0. So if we call this P, Q, and this will be R, the equation will be P plus, I should, Q plus R is equal to 0. We can rewrite this equation in this form: P plus Q is equal to 0 minus R. And we see that we are doing geometric operation of drawing a line on a curve to get 2 points connected to give us third point, but the third point is actually reflected to get the actual sum of these 2 points. Okay. The reason behind reflection is this law, that we add P plus Q and we add 0, 0, that is the point at infinity to R, and the point at infinity to R means we have to draw a vertical line, and together they are equal, so they intersect at this third point, which is, this point actually is the sum of P plus Q. And this is how we define group law. 2 points on elliptic curve added through this drawing secant lines and tangent lines will produce a third point on elliptic curve, and this is the group law. So there can be different possibilities that P and Q are distinct. There will be this point. We try to add Q with a tangent, that is adding P and Q plus Q, because tangent has this property of hitting the curve twice. And we can add any point to the spatial point. By the way, the operation here is again used as the same as the addition. Just don't get confused. This geometric addition is, we can use any symbol for addition. And this 0, by the way, this is point at infinity, not the usual 0 in the set of reals or integers or any other set. So this is how we define group law, and we add a point to itself, and we can even add the point to 0. So this is the fourth possibility. So this is these 4 pictures cover all the possibilities of addition of points on elliptic curves. Okay, so this group law, of course, this geometric approach is not very rigorous, but there is a whole algebraic approach when you take the equations and finding all the bits and itsy bitsy details to fill out, and you will see that this law actually works, that if you take 2 points and add them together, you will produce a third point, which is again on the elliptic curve. Zahid, can you play this video? And by the way, this the approach in here, you can observe that it makes no difference to add P to Q or P to Q or Q to P. So it makes no difference that same as Q plus P. We call this abelian groups. So this is an abelian group which has the same properties as the set of integers. And by the way, it is quite difficult to show the associative property of the addition law. So here is an example. Of course, example is not the proof, but we can see that how this law is associative. We add 7p plus p to get the same point as we add the other, So the one thing you can see from here is the abelian property or commutative property of this group. It makes no difference that we add p to 2 times p or 2 times p to p, because we are using the same tangent line or the secant line, so to get this the third point. And I think we should go further. So this was a bit about group law on elliptic curves, and if one might think that why elliptic curves are so important is there were a lot many other reasons for the importance of these elliptic curves, but I choose to take just three of them. And by the way, when you all of you have WhatsApp, right? All of you use WhatsApp. So what you see when you start to chat with someone, there is a small box which says that your chat and messages and calls are end-to-end encrypted. Have you ever wondered what this end-to-end encryption actually means? So the end-to-end encryption actually uses an elliptic curve of y square equals x cube plus some x square quantity, kind of this curve, y square equals x cube plus there is a large coefficient of x square plus x. So a curve of this type. And if you are interested to study more about these this elliptic curve, you can look up in the Google to curve 25519. So if you search this thing, or even if you search elliptic curve use in encryption of WhatsApp and blah blah, you just make the Google understand you, it will give you this elliptic curve with all the coefficients and all the algorithms how WhatsApp is using this elliptic curve cryptography to ensure that you and your Janu are having conversation without third person listening or stealing your scarlets that you are sending to your friend or any. Well, it's a whole semester or 2 semester course to understand the whole process of crypto, but I'm just here to count the importances. So, and the other important point regarding ellipticals is the Fermat's last theorem. They become the, as they call, the darling of number theory after Andrew Wiles proved Fermat's last theorem using elliptic curves. And they are also connected to congruent number. By the way, congruent number is a number which is area of a right triangle with integer or rational sides. This is, let's suppose, a right angle triangle, not very well drawn, but A and B. And for example, 6 is a congruent number because 6 is the area of our very famous 3, 4, 5 right triangle. When you find the area which is equal to half, area is equal to half of A times B, right? So half of A times B will be 6. So 6 is a congruent number, and it took a while to prove that 1 is not a congruent number by solving this curve y square equals x cube minus x, and showing that there are no rational points. So a lot more can be said about ellipticals, but we are trying to summarize. So there's another yet interesting point regarding the points on ellipticals. So as I started with rational numbers and I said that we will only focus on rational, or we will more focus on rational numbers, is that the elliptic curves contain rational points of very special shape. It cannot contain randomly chosen rational point, by the way. So as you can see, this is a page from my thesis, and if we choose x and y to be rational, A and C, such that A and C are co-prime, and a y, so the point actually is P, which is x, y, and x has this shape, A upon C, and y is B upon D. So we assume that C and D are non-zero. We can simply choose them to be positive, And we also assume that A and C are co-prime because we want this to be in the least form. So if any cancellation happens, we take it to the least form. Now we insert these 2 points in the equation. We are using the same equation, and we get this equation 2.11. Now simple divisibility rules can be applied to this equation, can show that c square divides d cube, and d cube divides c square, so they become equal. D square and c cube are same. Thus we set this ratio equal to E, and we find that C is equal to a square of a number and D is equal to cube of a number. So this C, this is square of a number, and this D, which is a cube of a number. So this point and elliptic curve becomes X, which was A divided by C, and Y, which is B divided by D, just becomes this type of A divided by square of a number, and this is B divided by cube of the same number. So it is really interesting to see that elliptic curves have coordinates, x coordinate containing square of a number, and y coordinate cube of a same number. We will see an example of this I think the next slide. So to this point, I try to explain all the ingredients necessary for the hunting process, or whatever you call it. So the grand connection is finally here. So what we do is we choose an elliptic curve E, let's call it E, and pick a rational point. By the way, it is there is no such algorithm which give you rational points on these elliptic curves. There is no algorithm till today that tells you that this elliptic curve even have rational points. So of course we have to choose certain elliptic curves which we know some rational points, or we start with a construction with elliptic curve, and this is the rational point and elliptic curve. So, and we do the same thing as we did in the sequence thing. We take multiples of a point. There's the same thing as timetable of 2 in the set of integers. So in any group you can take this kind of multiplication. So 2 was an element, we try to multiply 2 with all the natural numbers to get all the multiples of 2. So similarly we can take all the multiples of p, and we extract these denominators, and the denominators interestingly turn out to be the same sequences that we started with. Sometimes they turn out to be integers, sometimes they turn out to be the Fibonacci sequence, and more. So this is the elliptic curve that I chose. This is again a page from my thesis. So this is the elliptic curve that we choose, and the point which lie on this elliptic curve is 0, 0. This elliptic curve passes through the origin, and this is p, 2 times p. Of course we add these coordinates not with the geometric approach but the algebraic formulation, and there is a mathematical package called Sage which gives you a lot of formulas to work in if you are interested. So this is our original point, this is 2 times the point. We use the algebraic formulas to take the 2 times of the point, 3 times, 4, 5 and 6. So if this type of addition of a point to itself is quite easy. For example, if we want to find 8p, we can do this by multiplying or adding 3p to 5p, or if we have 4p and we try to double it 4p and add it to itself to get 8 times p. So it is the application of this algorithm is not very difficult. And if we extract all these denominators, now we see this is square of 3 and cube of 3, square of 2 and cube of 2, square of this number 195 and cube of 195, and so on and so forth. So the sequence that we get as a result of this process, this sequence is what we were hunting, and this is the natural habitat of this sequence. And there is a theorem which is called the Correspondence Theorem, that each sequence of this type, of course there is a sequence has a recurrence relation, and there is a non-linear recurrence relation which is satisfied by these equation, and all these recurrence sequences, these are called elliptic division sequences. I will explain why they are called division sequences in a minute, but if you these numbers are so gigantic that it's kind of difficult to show. So every sequence has an elliptic curve with a rational point, and every elliptic curve of this type with a rational point can produce a sequence like this. So it is kind of a bridge between combinatorics and geometry through the connection of group theory. So this was the whole explanation of the title of the talk, and I think I should show an example. If we start with this recurrence sequence, and we try to go to, there are many algorithms to get this elliptic curve and this rational point. Or if we start with this elliptic curve and this point on elliptic curve and do the addition and all the things, we are going to get this sequence. So there is a one-to-one correspondence between these sequences and elliptic curves, and all the problems that all the properties that elliptic curve enjoys, these sequences do enjoy the same properties, and all the challenges that are there regarding elliptic curves can be translated to sequences, and then you can play with sequences. So this is a way to connect two different islands of mathematics, which is combinatorics to geometry, through the route of group theory. So group theory is the bridge between combinatorics and geometry. So to summarize, we started with integers, we introduced sequences, elliptic curves, and we are back to integers, and we can loop it again, and if we start this again, we might get some other insights, but that was all for today. Thank you very much.
बड़े मज़े का लेक्चर था. अच्छा, तो इसमें कोई ऐसे सीक्वेंसेस मिले हमें इलिप्टिक कर्व से जो थोड़े कॉमन हो, क्योंकि ये तो काफ़ी रेयर किस्म के सीक्वेंसेस थे ना, पता नहीं माइनस पता नहीं मिलियन और प्लस ये कोई नॉर्मल वाले सीक्वेंस 2 4 6 8 का इलिप्टिक कर्व मिला है.
अच्छा, एक चीज़ जो मैं दरमियान में स्किप कर गया था वो था कि जो रिकरेंस रिलेशन ये एलिप्टिक सीक्वेंसेस सेटिस्फाई करते हैं. अच्छा, पहले तो मैं वो चीज़ बता दूं कि इनको एलिप्टिक डिवीजन सीक्वेंसेस क्यों कहा जाता है, और उनकी अपनी एक इम्पोर्टेंस है. यानी कि जो कम्बिनेटोरिक्स वाले पढ़ते हैं, सो दे स्टार्ट विथ लीनियर सीक्वेंसेस, फिबोनाची एंड ब्ला ब्ला, बट व्हेन दे इनकाउंटर नॉन लीनियर सीक्वेंसेस, दीज आर द फर्स्ट सीक्वेंसेस दे पुट देयर हैंड्स ऑन. और इनको डिवीजन सीक्वेंसेस कहने की एक वजह यह है कि let's take the example of Fibonacci sequence once again. 1 2 3 5 8 13. मुझे कुछ और लिखने पड़ेंगे. 21 34 and 55. So first Fibonacci, second, third, fourth, fifth. So notice that this is fifth Fibonacci number and this is 10th Fibonacci number. Okay, so this is fifth Fibonacci number and 10th Fibonacci number. So the division relation says that if nth Fibonacci number will divide f m to indices, will have the division property if n divides m. In this case 5 divides 10, so fifth Fibonacci number will divide the 10th Fibonacci number, and this is called the divisibility relation. And all the sequences that are connected to elliptic curves satisfies this relation. Okay, so this is kind of trivial to see in integers. Integers is also an elliptic division sequence. By the way, the recurrence sequence is quite long and messy with non-linear terms, which मैंने skip इसीलिए किया था कि उसको ना लिखूं. But वो sequence अगर आप जो आपका क्वेश्चन था कि जो नॉर्मल सीक्वेंसेस भी मिले हैं, तो द आंसर इज़ येस, बट अनफॉर्चुनेटली जो हमारे सिंपल सीक्वेंसेस है इंटीजर्स या फिबोनाची, ये सीक्वेंसेस एसोसिएट होते हैं ऐसे इलिप्टिक कर्व्स के साथ कि जो टेक्निकल सेंस में इलिप्टिक कर्व्स नहीं है, यानी कि वो स्मूथ नहीं है, कहीं उनके ऊपर सेल्फ इंटरसेक्शन है तो कहीं कोई और। मेनली जो है वो इस तरह के इक्वेशंस के साथ एसोसिएट है कि वाई क्यूब इज़ इक्वल टू एक्स क्यूब, इस तरह के। और इनके ऊपर रेशनल पॉइंट भी हमें मिल जाता है कि कौन से पॉइंट से हम स्टार्ट करें कि हम फिबोनाची सीक्वेंस जनरेट करें। जो एक छोटा मसला इसमें आता है वो ये आता है कि जो सिंगुलर इलिप्टिक कर्व्स है उनके ऊपर एडिशन लॉ थोड़ा सा टेक्निकली डिफरेंट है, जो हमने डिफ़ाइन किया है पॉइंट्स को लेके सीक्वेंस ड्रॉ करके, वो थोड़ा सा यहाँ पे लॉ डिफरेंट है।
जो वो था, हम कर रहे थे, ग्रुप बना रहे थे, वो यूं यूं करके जो कर रहे थे, वो मतलब उन्हीं में होते हैं जिनमें वो कस्प्स ना हो और
हाँ,
वो
तो
इंटरसेक्शन ना हो।
जो
स्मूथ।
हमारे सिंपल सीक्वेंसेस हैं उनमें ये है कि वो एसोसिएट होती हैं सिंगुलर इलिप्टिक कर्व्स के साथ, ठीक है। और ये जो सीक्वेंसेस है, अब जो रिकरेंस रिलेशन है वो फोर्थ ऑर्डर की नॉन लीनियर रिकरेंस रिलेशन है, तो इसकी ग्रोथ रेट बहुत हाई है। इसकी ग्रोथ रेट इज़ log ऑफ w टू n, यानी कि n स्क्वेयर। आप यूँ समझ लें कि जो फोर्थ टर्म होगी उसके या जो नाइन्थ टर्म होगी उसके अंदर यूँ समझ लें कि, सॉरी, आई एम फॉरगेटिंग द एक्चुअल लॉ विच इज़ log w टू n स्क्वेयर, शायद ये इनकी ग्रोथ लॉ है। nth टर्म या w n टर्म जो है, द साइज़ ऑफ w nth टर्म विल बी अप्रोक्सीमेटली दिस। तो इनकी ग्रोथ रेट बहुत हाई होती है। यही एक जो है टेक्निकल समझ लें कि प्रॉब्लम है कि दीज ग्रो सो रैपिडली दैट दे आर अनकंट्रोलेबल इन अ सेंस। खैर कंप्यूटर्स के लिए तो ये कंट्रोल में है, और कंप्यूटर्स जो है वो मोस्टली काम करते फाइनाइट, मोस्टली क्या कंप्यूटर्स करती हैं फाइनाइट फील्ड्स पे हैं, तो वो इतने बड़े हम फाइनाइट फील्ड्स भी नहीं लेते कि जिनसे ही बाहर निकल जाए सारी कहानी, तो उनमें रह के कंप्यूटेशंस हम कर सकते हैं। अच्छा, जो सॉरी एक चीज़ जो मैं भूल गया था वो ये कि जो इलिप्टिक कर्व हम लेते हैं इसका जो कोड नंबर है, ये इसकी जो प्राइम नंबर है 2 raised to power, एक सेकेंड यार चौक, सो विच इज़ 2 raised to power 255 -19। ये वो प्राइम नंबर है कि जिस फील्ड में हम रह के जो इलिप्टिक कर्व मैंने लिखी थी उसके साथ जो इंक्रिप्शन हम करेंगे तो वो व्हाट्सएप वाली इंक्रिप्शन, तो ये 25519 उस कर्व का समझ लें कि यहाँ से एक कोडिंग उसको दिया गया। तो
क्या क्या रिलेशन है इसके साथ?
जो जो मैंने बताया था कि जो इलिप्टिक कर्व यूज़ करते हैं इंक्रिप्शन के लिए व्हाट्सएप का, तो उसका जो नंबर था 25519 वो इस प्राइम नंबर का। अब इतना बड़ा नंबर है, इसको प्राइम प्रूव करना और फिर इसको यूज़ करके एक पूरा एल्गोरिथम जनरेट करना, इट्स अ यू नो क्वाइट चैलेंज। और यही खैर जो क्रिप्टो सिस्टम्स हैं उनमें इस तरह के चैलेंजेस को ओवरकम किया जाता है, लेकिन यहाँ पे जो इन नंबर्स के अंदर जो हमारे पास जो फ्रैक्शंस है वो अगला फ्रैक्शन तो इस पेज से बाहर जा रहा था, इसलिए मैंने उसको इग्नोर कर दिया। दीज आर सो जाइगेंटिक, यानी कि ये रेशनल नंबर्स बहुत ही भयानक किस्म के होते हैं। तो यही एक जो समझ लें कि ड्रॉबैक या मसला है कि इनकी ग्रोथ रेट बहुत ही हाई है, बहुत रैपिड ग्रोथ है।
बहुत अच्छी टॉक थी सज्जाद
सर थैंक यू।
तो ये जो रिलेशन है रेशनल पॉइंट्स और फिर जो ऊपर सीक्वेंस है, तो इनको किसी बहुत बड़े प्रॉब्लम पे वो हुए, यानी इनको यूज़ हुआ है, या जस्ट
अच्छा,
हम रेशनल बस हमने ये रिलेशन बना तो दिए, लेकिन क्या कहाँ पे यूज़ होते हैं?
बिल्कुल बिल्कुल। अच्छा, मज़े की बात ये बताऊं कि इस थ्योरी ऑफ सीक्वेंसेस को यूज़ करके ना कुछ इलिप्टिक कर्व क्रिप्टो सिस्टम्स कुछ ऐसे हैं कि जो इनके थ्रू जब हम अटैक करते हैं तो वो थोड़े से वीक हो जाते हैं। तो ये फ़ायदा हुआ कि हम कुछ इलिप्टिक कर्व क्रिप्टो सिस्टम्स को यूजिंग दिस थ्योरी ऑफ सीक्वेंसेस वी कैन काइंड ऑफ ब्रीच एंड ब्रेक देम। और मज़े की बात यह कि NSA जो नेशनल सिक्योरिटी एजेंसी अमेरिका में है, उसने अपनी वेबसाइट पे दिया होता है कि कौन कौन से आप इलिप्टिकल्स यूज़ कर सकते हैं। तो रिसेंटली कुछ इस तरह की टेक्निक जिनमें एक आध टेक्निक इनके भी शामिल थे कि जिन की मदद से कुछ इलिप्टिक कर्व्स को देखा कि यार इनको अगर इस अप्रोच से हम जाके पॉइंट्स फाइंड करें और उनके फिर अच्छा इलिप्टिक कर्व्स पे जो करते हैं एनकोडिंग वो कुछ इस तरह से करते हैं कि अब यहाँ पे एक पॉइंट को अपने ऊपर ऐड करना बहुत ही इजी है, ठीक है। तो हम क्या करते हैं कि एक पॉइंट को k टाइम्स अपने ऊपर ऐड करते हैं, ठीक, और एक नया पॉइंट हमें मिल जाता है q। अब जो फील्ड मैंने लिखा था 2⁵ -19 इतने बड़े फील्ड में आप हैं और k आपको फाइंड करना है। आपको p और q दोनों आपको दिए जाएंगे, इलिप्टिक कर्व भी वहाँ पे पड़ा हुआ है, पॉइंट भी पड़ा हुआ है। एक तो ये है कि आप स्टार्ट करें अभी, क़यामत से कुछ दिन पहले आपको ये मल्टीप्लिकेशन के बाद पॉइंट मिल जाएगा। तो ये तो हमने नहीं करना, हमने और यहाँ पे देखें ना जो एडिशन लॉ हमने डिफ़ाइन किया था उसमें हम हाफ नहीं कर सकते या पीछे नहीं जा सकते अनटिल कि अगर हमें पता चले कि एक पॉइंट दूसरे का डबल है, उसको हम यूज़ कर सकते हैं कि ये पॉइंट इसका डबल है। अदरवाइज़ द ओनली ट्रिक टू फाइंड दिस के डिस्क्रीट लॉग प्रॉब्लम का एलिप्टिक वर्जन है, डिस्क्रीट लॉग जो हम यूज़ करते हैं उसका। तो k टाइम्स p इज़ q, यू आर प्रोवाइडेड p एंड q, इलिप्टिक कर्व भी दिया है, p और q भी दिए हैं, बस आपको ये फाइंड करना है कि ये k क्या है। दिस k कंटेंस ऑल द इंफॉर्मेशन। तो कुछ इलिप्टिक कर्व्स ऐसे थे कि अब NSA ने अपनी वेबसाइट से रिमूव कर दिए कि इनको अगर आप यूज़ करेंगे तो हमारी ज़िम्मेदारी नहीं होगी। तो खैर यही इसका एक यूज़ था। एक राचेल शिप्सी एक रिसर्चर हैं, उनकी थीसिस में इसके और भी एप्लीकेशंस हैं, यानी कि पर्टिकुलरली इलिप्टिक डिवीजन सीक्वेंसेस के। और मैं उस बंदे का नाम मुझे याद नहीं आ रहा जिसने ये कहा था कि हम पूरी जो थ्योरी ऑफ इलिप्टिक कर्व्स उनको थ्योरी ऑफ सीक्वेंसेस पे लेके आ सकते हैं जस्ट बाय डूइंग दिस। तो यानी कि अगर आपको सीक्वेंसेस के साथ ही खेलना है तो पूरी थ्योरी को सीक्वेंसेस में लेके आएँ, सारा काम करें और काम 25 हो गया। Thank you very much once again for taking our time, and thank you TVH for providing this platform.